Thank you very much, Charlie, and thank you, Carlo and colleagues, for having us here. You can hear me well, I guess. So first, let me start by conveying regards from Max Reuter and Michael Buchwitz, who could not make it today. So therefore, it's now my pleasure to introduce to you one example of a satellite ECV, namely the greenhouse gas ECV, and show you how one of these car engines is working and what is inside it. So in most of the slides, you will have on the left side CO2, carbon dioxide, on the right side methane, CH4. And GHC has defined as the main application to improve our knowledge on the various natural and anthropogenic sources and sinks for those two trace gases. And immediately on both graphs, you can see over time that the concentrations are still increasing despite of all the political frameworks and agreements. So this is why they are relevant and why they are in the climate data store. I said that GHC is the starting point, defining the requirements, and this nice sentence, sufficient quality to estimate regional sources and sinks, means a very stringent requirement on the accuracy for the satellite-based measurements, so that modelers can then do inverse modeling to really understand the sources and sinks with these data. Since 2016, we have, based on these GHC requirements, a operational production of the greenhouse gas climate data records in the C3S, together with the associated documentation. To do so, there is a team, so I'm leading a larger lot that includes aerosols and ozone as other atmospheric composition variables. And then there is this greenhouse gas team, 4 institutes contributing, because we have a set of different products, different sensors, different algorithms, and you will hopefully understand better why this is the case. In the end, in this talk, we focus on a merged product, the so-called EMMA product, and you will see this later. Very essential element of a continuous operations, as we do it in C3S, is continued research and development. So what we have here in the C3S is based on many years of work that had been done in the ESA Climate Change Initiative, and it is still continued to meet new user requirements, to further improve the products, to better meet the existing user requirements. And there is another element to the data records that you will see. This is CAMS. The C3S is an offline reprocessing, so we usually go to the end of the last year, and then what happens in this year in quasi near real time is added by the atmosphere monitoring service. So now coming to the engine, what is happening in there? Of course, by theory, I think most of you will know, we have to do radiative transfer modeling, so we simulate the propagation of light through the atmosphere and to the Earth system and everything that happens in there. And we have to consider in such simulations not only CO2 and methane, but also water vapor and other gases and constituents that influence the signal. And then in the retrieval, we have to fix the assumptions on our target gases and other quantities influencing the signal with optimal estimation algorithms to best fit these radiative transfer forward modeling. And this is a complex task. Therefore, there are different solutions. We have different algorithms with different assumptions, simplifications, parameterizations. And for each of them, there is documentation. So there is traceability and transparency to what we do. And then, on top of this, to make life easier for many users, for those that can work with such a kind of product, there is then an emerging algorithm. And this merging algorithm, EMMA, that I'm now describing slightly, is picking one individual measurement from one of the multiple records that we have by the median approach. So there is not a blending of different measurements. This is always what users do not like. We can also transfer all the averaging kernel and the uncertainty information directly for each measurement point. The data that are going into this is what is produced in the C3S but there is also data from Japan and from the US, which are added in, and reference data. And then there is a harmonization step where a common a priori is used to do some offset correction. I will show in the next slide. Finally, a gridding and this median selection on this gridded data set, and then the product generation where these chosen best data points are combined into the final data record. So I promised you I will show you a bit on this harmonization. So you see here, for example, on the left for CO2, the different data sets over time from 2003 to now, starting with Skiamaki in the beginning, and then with GOSAT, OCO2, and GOSAT2, several algorithms for those three instruments. So the number of contributing data sets is here. And you see here the individual records as they are. So happily, they are similar. They are not perfectly equal. That's why we have them more than one, but they are similar. But in the case of methane, you see here the offset correction brings, for example, the bluish ones and the rest better together. So there is a need for this step. And then we get this kind of product, the first graphical representation. So you see again in latitude bands over time, CO2 and methane. Then you see the uncertainties associated. So for many users, this is a relevant information. You see that changes in the Skiamaki data quality have impacted, even with a stepwise change here, the uncertainties. And you see the number of observations. So with OCO2, there is a higher frequency of observations added. Of course, this cannot blend everything, technical capabilities and limitations of each of the sensors, but this will help to create this best of all data set. And now I come back to this, what I showed smaller in the beginning. So again, you see the different sensors that went into it and ensembles of different algorithms. And yes, we see for CO2 a continuous increase, the annual cycle, which is more pronounced in the northern hemisphere in red than in the southern hemisphere in green. And for methane, you see the same, maybe not as a continuous increase, but increase and then even steeper increase. So this is then the outcome of this merging algorithm. And this is not the output that is used by the inverse modeling groups, because they prefer to have the individual data products which are self-consistent across the whole globe. But to do this trend analysis, such a blended record is the choice. Yeah, another essential step in every satellite climate data record creation is the validation. So the comparison to external reference data sets. And you see here a rather complex slide, but for one quality parameter, you see here different individual products with 3 different validation methods, and always on the right is this EMMA product. So in the upper panel, this is the random error, which should be smallest. EMMA is the smallest. The accuracy, EMMA has the smallest range of possible values. And if you look across those different panels, EMMA has the highest data quality in this kind of comparisons. And that is why it is a valuable addition to the portfolio that we have. So then the final content slide before my summary. A first application of these kind of data sets. You see here in the upper part again the time record, and here you see annual growth rates. It's not such a simple calculation to get from the first to the second, but take this as the result. So for CO2 you see some variation from year to year, but it's more or less a constant increase despite of all the political agreements. For methane, there is something happening in the last 2 years. And this is the focus of ongoing research. So there are hypotheses around, like this could be natural emissions in the tropics or a reduced OH, self-cleaning capacity. But far from having understood and having completed this kind of scientific assessments. So this brings me to my conclusion. I want to stress that this data set, EMMA, integrated from 2003 to now, is the longest available from all this suite of different satellite algorithms and satellite products. And as I already explained before, the best product depends on the application. So different application cases, different users may need one of the individual algorithms or this merged algorithm as their preferred choice. So with this, I'm open to a question if there's time, and thank you very much.
Let us indeed see if there's a question in the room that can be answered quickly. Raise your hand. Since there's no first question, is there a second question? Yes, Carl.
I hope I can answer it, not being
I think it's a very open-ended question. So, on this rise in CO2, what is your feel? Because we are asked day in, day out, what is the reason for that? So you suggested a few...
In methane?
Sorry, in methane.
CO2,
yes.
it's our emissions.
I meant methane, yeah.
I'm not the expert, but from what I know, the complexity of natural and anthropogenic emissions is hidden in here, and disentangling this to really come to a conclusion. It's open research, so I don't really speculate on what I think is the best.
We have time for one more quick one. Eddie, go for it.
Are we any closer to being able to retrieve accurate isotopic ratios to detect sources of methane, particularly, but also with CO2? And apologies if that's what Carlos just asked.
I'm not sure I understand the question.
Maybe repeat the question.
Are we getting any closer to retrieving isotopic ratios of CH4 and CO2 such that we can trace that back to the emission sources?
Honestly, I cannot answer this question.
Okay.
So I can consult back to Michael and Max, but I would not do you a good job trying to answer. Yeah. Okay.
Thomas, thank you so much for your contribution.